concrete members. Okay? And those tables in ACI look like this. So minimum thickness for solid non-pre-stressed one-way slabs. If the minimum thickness is L over 20, that means let's say we have whatever, let's say 10 feet or 10 meters, whatever. 10 meter slab is very difficult to design, but let's say 4 meters span. 4 meter span, 4,000 over 20, so 80 millimeter. Is that right? Probably. Something like that. So depending on your thickness, depending on your span, whatever is the span divided by 20 will give you minimum thickness. So that's for one-way slabs. Simply supported span L over 20. What about simply supported beams? The thickness, minimum thickness needs to be L over 16. So if this is satisfied, you don't have to do any deflection checks. That's one approach. This is the easier approach. The other approach is to actually calculate the deflections. So it's a little bit more complicated for FRP beams because we have variable stiffness and the nature of the FRP beams is brittle. That means it can fail all of a sudden. So the bond between bars and the surrounding concrete is also not so good. So we really cannot apply steel beam equations to FRP reinforced beams. The second thing which is very, very important is ACI 440.1R tells you don't use minimum thickness as your basis for deflection control. That means the two methods we had for steel reinforced concrete beams, one method was satisfying the minimum thickness requirements. That method is not valid for FRP. Okay, so that's an important difference. However, ACI 440.1R still gives you the minimum thickness recommendations, but that's only for preliminary design. For final design, you cannot use those minimum thickness requirements and say deflection is satisfied. Okay, so that's very, very important difference. So you must use the detailed method for calculating deflections. For your preliminary designs, the thickness limits for one-way slabs and beams is for simply supported beams. Slabs, the minimum thickness is L over 13. And for beams, it's L over 10. Again, I want to emphasize this. This table is only for guidance because they tell you don't use this table, but they are giving the table anyway. Just for you, that will be a starting point actually. And then you do the actual detailed calculation. You must do the detailed calculations. Okay? So there is a big difference between this and steel reinforced concrete. For steel reinforced concrete, that was L over 20, right? For slabs, and L over 16 for beams. Here it is L over 13 for slabs and L over 10 for beams. But this is only for guidance. It's not to be used as the final design check. So we'll use what's known as effective moment of inertia in our calculations. So our moment of inertia of the beam would be under service load condition. This is one thing you must remember. Our strength limit state, we always use factors, right? Under serviceability limit state, our factors are different. They are normally 1, right? You remember? Except for wind and other things, you use 0.8. But for dead load and live load, our factors are 1 and 1. Am I right? At least in ACI, that's what it is. So for unfactored service load condition, you need to find out the moment of inertia corresponding to different levels of loading. So there are two extremes. One is if the section is uncracked, you will use gross area and moment of inertia of the uncracked section. That's I sub G. I sub CR is under cracked condition. So that will give you very small or small moment of inertia. I sub G, which is based on uncracked section, will give you larger moment of inertia. So there is a larger moment of inertia, a smaller moment of inertia, depending on how much is your service load moment relative to cracking moment. Service load moment relative to cracking moment, your moment of inertia will be somewhere in between these two values. And what we are going to do here is to find out that effective moment of inertia. That's what we are going to do. So to find out I sub CR under cracked condition, it's a very simple expression. I'm sure you can. Most of the books in Indian codes or following Indian codes will have same or similar equation for reinforced concrete, steel reinforced concrete. Similar equation. This can be quite easily derived. Actually, in my notes I have the derivation of all these equations. But here I just show you the final equation. So what is I sub CR? I sub CR equals B for a rectangular beam. It's B times D cube over 3 times K cube, which is the neutral axis factor under elastic condition, elastic cracked condition, plus NF AF times D square times 1 minus K square. And that K factor, which is the neutral axis depth factor, depth to neutral axis factor, K equals square root of 2 rho F. Rho F is steel, not steel, but FRP reinforcement ratio. NF is modular ratio. What is modular ratio? I don't think I have it here, but NF is the NF is what's known as and that's equal to EF over EC. EF is the modulus of FRP, EC is the modulus of concrete. So by Indian standard, what is EC? Does anyone remember? 5,000 square root of F prime CK. Is that right? Very good. In American standard, that is 57,000 square root of F prime C, where F prime C is in PSI units. PSI units, and the modulus also is in PSI units. All right. So there is a minor difference. You will see there is a difference between this and this. When you calculate the number, you plug in the numbers, you will see there is a difference. Okay. But we know that there is a difference. We will use ACI equations in all of this, because whenever you are designing anything, from start to end, use the same standard. Use entirely Indian standard or entirely ACI standard. Don't use half of this and half of this. That will become very inconsistent. Okay? So mixed mode is not necessarily good. So NF is modular ratio, plug in here, that's it, and then you get your K. Once you get your K, you can find out I sub CR. This K can be plugged in here to find out I sub CR. Everything is so simple, you can plug into your Excel spreadsheets and you get your numbers. It's such a simple task. And of course the stiffness due to effective moment of inertia is somewhere between stiffness of the cracked section and stiffness of the gross section, that is uncracked section. All right, so finally we are almost there. We are getting there. The effective moment of inertia is I sub E, and that's equal to I sub CR over 1 minus gamma times M sub CR over MA squared times 1 minus I sub CR over IG. In any case, this must be less than I sub G. So this is a new equation which came into effect recently. So if you are looking at older versions, this won't match with the older version of ACI 440.1R. Okay, so this is a new one. So use this only, because there are some problems, like when you see that the equations that are in the ACI code at the time of its publication are not working, people change. So every time it is updated. So this is the latest revised equation. So in this expression, gamma equals 1.72 minus 0.72 MCR over MA, where MCR is the cracking moment and MA is the service load moment for which you are finding out the deflection. Okay, very simple, very straightforward. Now, M sub CR. How do you find out M sub CR? M sub CR is based on ICR, that's correct, and it's based on modulus of rupture, right? That's the flexural tensile strength, modulus of rupture. I'm not sure in IS code they call it modulus of rupture, but that's what it is. And I sub, I'm sorry, somebody said it's based on I sub CR. I said yes, but that's not correct. It's not correct. It's based on gross moment of inertia of the gross section. So correction, my correction. It's not based on I sub CR. It's based on I sub G, which will give you the moment at which the first crack appears in your concrete section. Okay? So F sub R is 7.5 square root of F prime. See, there is a lambda here. Lambda is based on the type of concrete. If you have lightweight concrete, it's 0.7. If it is, 0.85, it's all lightweight concrete, it's 0.7 or 0.75. For normal weight concrete, lambda equals 1. So if you are designing a normal weight concrete, you can forget about lambda. So this is in PSI units. The corresponding SI units equation is right here, 0.62 times lambda times square root of F prime C I sub G over YT. So that's your M sub CR. And this is based on modulus of rupture, right? What is the modulus of rupture in IS standard? IS 4, how much? 0.75 times square root of F prime CK? Yeah, okay, 0.7. So in US, in ACI 318, it is 7.5 square root of F prime C, but F prime C is in PSI units, so that's the difference. So anyway, you will use this equation in SI units. I sub G is the moment of inertia of uncracked section, which is the gross section without any cracks. So we need to find out both short-term and long-term deflections based on this method, and you apply service loads. Many times students, not experienced professors like you all, they make a mistake in terms of loads always, because if you are using, particularly if you are using a program, fancy program, you plug in all the load factors and then you come back and say, oh, my deflections are not working. They're not working because you are using factor loads. In case of Indian standard, it's 1.5 dead load, 1.5 live load, right? That means the factors, the deflection will be increased by a factor of 1.5 if you are using factor loads for calculating deflections. That's not what it's supposed to be. You should use service loads which will not have any factors. So use service loads, and then we need to find out the sustained load effects as well. So we will use sustained load contributions and we'll calculate the long-term effects. So we'll use the effective moment of inertia to find out instantaneous or immediate, that's what it's known as, immediate or instantaneous or short-term deflections. All three mean the same thing. Immediate, instantaneous, short-term deflection, all three mean the same thing. They are calculated based on I sub E. And then you compare those with the maximum allowed deflections. So most of the mechanics books will have these deflection equations, right? Depending on the type of load you have most common one is delta equals 5 WL4 over 384 EI. Very standard equation. You probably, most of you who teach mechanics, you probably remember these numbers or these expressions. And what do you compare those with? You compare those with the maximum allowed. Maybe you cannot see from the last last rows, but here I have L over 180 for immediate deflection due to maximum roof load or snow load or rain load. Okay, that's for flat roofs. For roofs and floors, it is 480, L over 480. That's considered to be reasonably standard. Sometimes each client will have their own design basis. They will say use L over 360 or use L over 500, whatever. But ACI recommends, it's not a requirement, but it's a recommendation, L over 480, where the partitions can be damaged. Where the partitions cannot be damaged or they are not at risk, use L over 250. Okay, so once you have calculated the deflections, you need to find out the long-term effects. And the deflections, of course, will depend on member geometry, amount of reinforcement you have, member size, loads, and all these things that you know really well. Creep and shrinkage of concrete, cracking, and creep rupture of FRP. That's a very important aspect we have to deal with in our FRP design. So I don't know how many of you are familiar with this plot, because this is a very simplified version of long-term deflections as given in ACI 318. So many of the ACI requirements are very, very simplified. So this is one of them. So on the x-axis you have time in years, on the y-axis you have deflection. So if you apply a load, the moment you apply the load, you will have some amount of initial deflection, delta I, which is also instantaneous deflection, immediate deflection, and I think they call it immediate deflection these days. And then with time, if you are maintaining the same load, if you are sustaining the load on the member, then there will be increase, and that will increase by a factor which is zeta over 1 plus 50 rho prime. So this factor, zeta over 1 plus 50 rho prime, needs to be added to your delta I. So zeta has some values. I will show you those values in a minute, the recommended values. Rho prime is the area steel ratio of compression steel. Steel ratio of compression steel. For FRP, what would that be? 0. Okay? Because if you have FRP reinforcement in compression area, you don't count on those, any contribution from FRP. So that's 0. So we can remove this. So we are left with only zeta times delta I. So ACI tells you for creep and shrinkage, use lambda delta, which is zeta over 1 plus 50 rho prime F, but rho prime F is 0, therefore we'll just use lambda delta equals zeta. So I can plug this in here and then get long-term effects due to sustained load. Now what is zeta? Zeta is for up to 3 months of loading, you can use zeta equals 1. That means there is no increase in the deflection.